Right now, electricity is flowing through your body, not from batteries or power lines, but from minerals, electrolytes, that carry electrical charge through every cell. These aren't just supplements and sports drinks, they're the power source for life itself. That heartbeat you hear, it's powered by electrolytes. The thoughts in your brain, electrolytes. Every muscle movement, electrolytes again. From sodium to potassium, from calcium to magnesium, these charged particles orchestrate an intricate dance that keeps you alive. We'll explore how these star-forged elements became essential for life, why your body maintains such precise control over them, and what happens when this delicate balance gets disrupted. From cellular communication to muscle function, from nerve transmission to pH balance, we'll discover how electrolytes make it all possible. I'm Eric Johnston, and while I'm no biochemist, I am fascinated by how these charged particles orchestrate life itself. On this episode of Food Truth, we're diving into the electrical system that powers your body. Join me as we discover why you're not just a water-based organism, you're an electrically powered being, running on star-forged ions, performing an endless, life-sustaining dance. This is the Electrolyte Show. The journey of electrolytes through the human body is a remarkable process of absorption, distribution, and utilization that occurs continuously to maintain vital bodily functions. Understanding this process begins at the point of ingestion, where electrolytes enter our system through food and beverages. The complexity of this system becomes apparent when we consider that different electrolytes follow distinct absorption pathways and timing patterns. When electrolytes first enter the mouth, the digestion process begins immediately. Salivary enzymes start breaking down food, while the presence of sodium and potassium in our saliva helps initiate the taste signaling process. The salivary glands secrete approximately 1.5 liters of saliva daily, containing precise concentrations of sodium, potassium, chloride, and bicarbonate ions that begin the digestive process and protect oral health. The stomach's highly acidic environment plays a crucial role in electrolyte processing. Here, hydrochloric acid not only aids in breaking down food, but also creates an optimal environment for mineral dissolution. The stomach's acid-base balance, maintained by various electrolytes, ensures proper enzyme function and nutrient breakdown. Parietal cells in the stomach wall actively pump hydrogen and chloride ions into the stomach lumen, creating the acidic environment necessary for proper digestion. As the partially digested food moves into the small intestine, the most significant phase of electrolyte absorption begins. Different sections of the small intestine specialize in absorbing specific electrolytes. The duodenum primarily absorbs calcium and iron, while the jejunum and ileum are particularly efficient at absorbing sodium, potassium, and chloride through both active and passive transport mechanisms. This specialization ensures maximum absorption efficiency and prevents competition between different minerals. The process of active transport is particularly fascinating, as it requires specific carrier proteins and energy in the form of ATP. Sodium-potassium pumps work tirelessly across cell membranes, maintaining crucial concentration gradients. This process is so important that it consumes approximately 25% of your body's resting energy expenditure. Each cell contains thousands of these pumps, working continuously to maintain proper electrolyte balance. The role of transport proteins extends beyond simple absorption. Specialized channels and carriers exist for each major electrolyte, with some requiring co-transport with other molecules. For instance, sodium-dependent glucose transporters, or SGLTs, couple glucose absorption with sodium transport, making this process more efficient. Similar mechanisms exist for amino acids and other nutrients. The intestinal absorption of calcium follows a particularly complex pathway involving both vitamin D-dependent active transport and passive diffusion. The efficiency of calcium absorption varies significantly based on factors such as age, hormonal status, and vitamin D levels. This process is carefully regulated to maintain proper bone health and cellular function. Magnesium absorption occurs primarily in the small intestine through both transcellular and paracellular pathways. The efficiency of magnesium absorption is inversely related to intake, with the body absorbing a higher percentage when dietary intake is low. This adaptive mechanism helps maintain adequate magnesium levels even when dietary sources are limited. Once absorbed, electrolytes enter the bloodstream, where they begin their journey throughout the body. The distribution phase is carefully regulated by hormones like aldosterone and antidiuretic hormone, which help maintain proper electrolyte concentrations in different body compartments. This hormonal control ensures that each tissue receives the appropriate amount of each electrolyte. The role of the endocrine system in electrolyte regulation cannot be overstated. Parathyroid hormone regulates calcium and phosphate balance, while aldosterone controls sodium and potassium levels. These hormones work in concert with other regulatory mechanisms to maintain homeostasis across various body systems. Cellular uptake of electrolytes varies by tissue type and immediate physiological needs. Muscle cells, for instance, may rapidly absorb potassium during exercise, while nerve cells maintain precise sodium and potassium gradients for proper signal transmission. This tissue-specific regulation allows for optimal function across different organ systems. The distribution of electrolytes between intracellular and extracellular components is critical for proper cell function. Approximately 98% of body potassium is found inside cells, while sodium is primarily concentrated in extracellular fluid. This distribution is essential for maintaining proper cell volume and function. The kidneys serve as the body's primary regulators of electrolyte balance, constantly filtering and reabsorbing these minerals. Each day, your kidneys filter approximately 180 liters of plasma, reabsorbing needed electrolytes and excreting excess amounts based on the body's needs. This process involves multiple specialized segments of the nephron, each designed to handle specific aspects of electrolyte regulation. The proximal tubule of the kidney reabsorbs about 65% of filtered sodium and water, along with proportional amounts of other electrolytes. The loop of Henle creates concentration gradients that allow for water conservation, while the distal tubule and collecting duct provide fine-tuning of electrolyte excretion under hormonal control. Homeostatic mechanisms continuously monitor electrolyte levels through specialized sensors throughout the body. These include osmoreceptors in the hypothalamus and baroreceptors in blood vessels, which trigger appropriate responses to maintain optimal electrolyte concentrations. This monitoring system operates 24/7, making constant adjustments to maintain balance. The role of the nervous system in electrolyte regulation includes both direct and indirect mechanisms. The sympathetic nervous system can influence kidney function and electrolyte excretion, while also affecting sweat gland activity and gastrointestinal motility, all of which impact electrolyte balance. Factors like physical activity, climate, and dietary intake can significantly impact the rate and efficiency of electrolyte processing. During exercise, increased sweating leads to electrolyte losses that must be compensated for through the adjusted absorption and retention mechanisms. The body's adaptation to these challenges involves multiple regulatory systems working in concert. The composition of sweat varies based on factors such as fitness level, acclimatization, and hydration status. Athletes may lose significant amounts of sodium through sweat, requiring careful attention to replacement strategies during prolonged exercise or in hot conditions. Dynamic equilibrium between various body compartments ensures that electrolytes are available where needed. This includes exchanges between intracellular and extracellular fluids, as well as specialized compartments like cerebral spinal fluid and joint fluid. The maintenance of these gradients is essential for proper nerve conduction, muscle contraction, and cellular function. The interplay between different electrolytes adds another layer of complexity to their nutrikinetics. For example, calcium and magnesium often compete for absorption, while sodium and potassium levels must be balanced for proper cell function. Understanding these interactions is crucial for optimal supplementation strategies. The efficiency of electrolyte nutrikinetics can be affected by various factors, including age, medications, and certain medical conditions. Understanding these influences helps in optimizing electrolyte intake and absorption for different populations. For instance, older adults may have reduced absorption efficiency and require adjusted intake recommendations. Certain medications, particularly diuretics and corticosteroids, can significantly impact electrolyte balance by affecting kidney function or hormonal regulation. These effects must be considered when developing treatment plans and dietary recommendations. Various disease states can affect electrolyte nutrikinetics. Conditions affecting the gastrointestinal tract may impair absorption, while kidney disease can disrupt normal regulatory mechanisms. Understanding these pathological influences is crucial for proper medical management. Recent research has revealed new aspects of electrolyte regulation, including the role of the microbiome in mineral absorption and the influence of circadian rhythms on electrolyte handling. These discoveries continue to expand our understanding of this complex system and may lead to improved therapeutic approaches. Modern analytical techniques have enhanced our ability to study electrolyte nutrikinetics in real time. Technologies such as isotope tracing and advanced imaging methods provide detailed insights into the movement and distribution of electrolytes throughout the body. Looking ahead, personalized approaches to electrolyte supplementation based on individual genetic profiles, activity levels, and health status may become more common. This precision nutrition approach could optimize electrolyte balance for each person's unique needs and circumstances. The timing of electrolyte absorption and utilization follows distinct patterns throughout the day. Circadian rhythms influence both the efficiency of absorption and the body's electrolyte needs. For example, aldosterone levels typically peak in the early morning hours, affecting sodium retention and potassium excretion patterns. The impact of dietary composition on electrolyte absorption deserves special attention. High fiber diets can affect mineral availability through binding and chelation, while protein intake influences calcium absorption and excretion. Understanding these nutritional interactions helps optimize dietary recommendations for different populations. Exercise intensity creates unique patterns in electrolyte flux. During high intensity exercise, rapid shifts occur between intracellular and extracellular compartments, particularly with potassium. These acute changes must be carefully managed to maintain performance and prevent complications. The role of electrolytes in cellular signaling extends beyond basic concentration gradients. Calcium, in particular, serves as a crucial second messenger in numerous cellular pathways. These signaling cascades influence everything from muscle contraction to hormone secretion and neural transmission. Environmental factors can significantly impact electrolyte balance through multiple mechanisms. High altitude exposure, for instance, triggers complex adaptations in fluid and electrolyte handling, while heat acclimatization leads to changes in sweat composition and kidney function. Different age groups show distinct patterns in electrolyte handling. Infants and young children have higher turnover rates and different regulatory mechanisms compared to adults. Understanding these age-related differences is crucial for appropriate supplementation and medical management. The interaction between hydration status and electrolyte balance represents a complex dynamic relationship. Changes in hydration can affect electrolyte concentrations both directly through dilution or concentration effects and indirectly through hormonal responses. Recovery from electrolyte imbalances follows predictable but individual-specific patterns. The time course of normalization depends on factors such as the severity of the imbalance, kidney function, and the body's overall regulatory capacity. All right, now we're going to trace a banana's journey from the moment you take a bite all the way up to cellular utilization of the potassium. So, at minute 0 through 5, the initial digestion begins. The banana enters your mouth and mechanical breakdown begins through chewing. Then salivary amylase starts breaking down carbohydrates. The potassium ions, symbolized by a K and a plus symbol, begin disassociating from the banana tissue matrix. The average banana, of course, contains around 420 milligrams of potassium in readily dissociable forms. The swallowing then moves the banana bolus through your esophagus and into your stomach, where in minutes 5 through 30, the stomach processing begins. There, you have your hydrochloric acid further breaking down your banana matrix. There's a pH balance of about 1.5 to 3.5, which is helping release the bound up potassium into your digestive system. You continue the mechanical churning of the tissue breakdown of the banana, and the potassium becomes increasingly available in ionic form. There's a little bit of potassium absorption occurring in the stomach, but that doesn't really start up until we get into the small intestines. Then at minutes 30 through 90, we actually go into the banana bolus then is now partially broken down, and it enters something called the duodenum. That's the beginning of the small intestine. There, your pancreatic enzymes are going to break down the remaining matrix of the banana even further. Then the first significant amount of potassium absorption is actually starting to begin here. The actual initial absorption, it's occurring through something called passive diffusion. And then active transport mechanisms activate based on the concentration gradients. After about an hour and a half, the maximum potassium absorption occurs in the jejunum and the ileum, the second part of the small intestine. Approximately now, there's about 90% of available potassium is being absorbed. The transport occurs through both passive and active mechanisms. I think it's about 80% of uptake is passive, and around 20% of the potassium intake is active transcellular transport. The absorption rate, you're getting about 10 to 15 milligrams of potassium absorption per minute. Your cellular sodium potassium pumps are actively maintaining your gradients at this time. 2 to 4 hours after taking that bite of banana, you've now absorbed a lot of potassium, and it's entering what's called portal circulation. You're getting an initial spike in plasma potassium levels. And remember, that takes about 2 hours after you've eaten the banana. You're getting some hormonal responses, including insulin is being released to help drive potassium into cells, and aldosterone levels are adjusting if necessary. Your cellular uptake, of course, is happening across all body tissues, but the priority is given to the muscles. So the maintenance of plasma for the K plus symbol is starting to fall within normal range. And now at about 4 hours to 24 hours after that bite of banana, you have what's called steady state distribution, which is the potassium has been pretty much distributed to all the tissues and organs that it's going to be distributed to. Any excess potassium at this point has been filtered out by your kidneys, and you're now in your fine tuning phase to achieve homeostasis. So that's just where everything's in balance, and that happens because the kidneys are adjusting their excretion. All your cells are continuing to exchange. Your hormone levels have normalized, and everything has been completely integrated as far as potassium into your cells and organs again. Throughout history, diverse cultures developed sophisticated understanding of mineral balance in the body, even without modern scientific terminology. From the salt tablets of Roman legions to the mineral-rich hot springs of Japanese onsen, traditional healing practices recognized the vital role of what we now call electrolytes. Traditional Chinese medicine views electrolyte balance through the lens of yin and yang, using specific herbs and minerals to restore harmony in the body. Practitioners historically used combinations of minerals like salt, potassium-rich herbs, and mineral springs to treat various conditions, particularly during seasons of extreme weather or physical exertion. Indigenous peoples worldwide developed remarkable insights into mineral balance through careful observation and generational knowledge. Native American tribes identified mineral-rich springs and clay deposits, using them for healing purposes, while Pacific Islander cultures recognized the importance of coconut water for hydration during illness. Persian traditional medicine, particularly during the Golden Age of Islam, developed sophisticated understandings of mineral balance and health. Scholars documented specific mineral treatments and their effects on the body, many of which align with modern understanding of electrolyte function. Modern research continues to validate many of these traditional approaches, revealing scientific mechanisms behind ancient practices. Studies of traditional remedies often uncover precise electrolyte ratios and combinations that prove effective in maintaining health, bridging ancient wisdom with contemporary medical understanding. Modern medical technology relies heavily on precise electrolyte measurement and manipulation, from basic blood tests to complex treatments. Advanced biosensors can now monitor electrolyte levels in real time, enabling faster and more accurate medical interventions. The development of specialized electrolyte solutions has revolutionized emergency medicine and surgical care. These carefully balanced fluids, from simple saline to complex multi electrolyte solutions, save countless lives by maintaining crucial mineral balance during critical medical procedures. Dialysis technology represents one of the most sophisticated applications of electrolyte science in medicine. These systems carefully filter and balance electrolytes in patients with kidney failure, requiring precise control of multiple mineral concentrations simultaneously. Electrolyte sensitive imaging techniques have transformed diagnostic medicine. Contrast agents containing specific electrolytes enabled detailed visualization of body structures and functions, while ion sensitive MRI techniques provide new insights into cellular processes. The emergence of bioelectric medicine uses controlled electrolyte gradients to influence cellular behavior and promote healing. This growing field explores applications from wound healing to cancer treatment based on understanding how cells respond to changes in their ionic environment. Wearable technology for electrolyte monitoring is advancing rapidly, with new devices capable of measuring sweat composition and providing real time feedback about hydration and mineral balance. These innovations are particularly valuable for athletes, patients with chronic conditions, and healthcare monitoring. Ocean salinity patterns serve as crucial indicators of climate change, with shifting electrolyte concentrations affecting global weather patterns and marine ecosystems. These changes influence everything from ocean currents to the distribution of marine life, making them key markers of environmental transformation. Soil electrolyte balance plays a fundamental role in agricultural productivity and ecosystem health. Changes in soil mineral composition, often due to agricultural practices or environmental pollution, can dramatically affect plant growth and microbial communities essential for soil fertility. Freshwater systems depend on precise electrolyte balances, even with small changes affecting aquatic life and water quality. Urban development and industrial activities often disrupt these balances, leading to cascading effects throughout freshwater ecosystems. Atmospheric electrolytes influence weather patterns through their role in cloud formation and precipitation. Changes in atmospheric ionic composition, partly due to pollution and industrial emissions, can affect regional weather patterns and contribute to climate variability. The interaction between electrolytes and environmental pollutants creates complex challenges for ecosystem management. Heavy metals and other pollutants can disrupt natural electrolyte cycles, affecting everything from soil chemistry to aquatic food webs. Global climate change is altering electrolyte distributions across multiple ecosystems simultaneously. Rising sea levels introduced saltwater to coastal freshwater systems, while changing precipitation patterns affect soil mineral composition, creating new challenges for environmental conservationists and agriculturalists. Your body's electrolyte needs fluctuate throughout the day based on activity level, diet, climate, and various physiological factors. Understanding these patterns can help you maintain optimal electrolyte balance without overthinking it. Most people can maintain healthy electrolyte levels through a balanced diet rich in fruits, vegetables, and minimally processed foods. Key sources include bananas for potassium, dairy products for calcium, and table salt for sodium and chloride. Common situations that require extra attention to electrolyte balance include intense exercise, illness with fever or gastrointestinal symptoms, alcohol consumption, and exposure to high temperatures. In these cases, deliberate electrolyte replacement may be necessary. Certain medications, particularly diuretics and some blood pressure medications, can significantly affect electrolyte levels. Working with healthcare providers to monitor and adjust electrolyte intake becomes crucial for people on these types of medicines. Signs of electrolyte imbalance can be subtle but important to recognize. These may include muscle cramps, fatigue, headaches, or changes in blood pressure. Knowing these warning signs helps in taking prompt corrective action. The key to daily electrolyte management lies in consistency rather than overcorrection. Small, regular adjustments to diet and fluid intake are typically more effective than dramatic intervention. Movement of electrolytes across cell membranes enables muscle contractions and nerve signaling, making them crucial for every aspect of athletic performance. The balance of sodium, potassium, and calcium particularly affects muscle function and recovery. Athletes lose electrolytes primarily through sweat, with losses varying significantly based on factors like temperature, humidity, exercise intensity, and individual physiology. A typical athlete might lose 500 to 1500 milligrams of sodium per hour of intense exercise. Different sports require different electrolyte replacement strategies. Endurance athletes often need more aggressive replacement than those in strength or skill based sports, while timing of replacement can be as important as quantity. Recent research has shown that personalized electrolyte replacement strategies based on individual sweat analysis can improve performance and reduce the risk of exercise associated conditions caused by drinking too much plain water during extended exercise. The preloading of electrolytes before competition has become a common practice among elite athletes. This strategy helps ensure optimal levels at the start of activity and can delay the onset of fatigue. Post exercise electrolyte replacement plays a crucial role in recovery, affecting everything from muscle repair to glycogen replenishment. The window immediately following exercise presents a prime opportunity for effective replenishment. Understanding of electrolytes began with ancient observation of salt's preservation properties and medicinal uses, but scientific understanding emerged in the late 18th century with Galvani's famous experiments with frog legs and electrical current. The 19th century brought breakthrough discoveries about ion transport and membrane potentials. Scientists like Emile Dubois-Raymond and Walter Nernst developed fundamental theories about how electrolytes function in biological systems. Sidney Ringer's development of Ringer's solution in the 1880s marked a pivotal moment in medical history. His work demonstrated the importance of specific electrolyte ratios for maintaining tissue function and laid the groundwork for modern intravenous fluid therapy. The mid 20th century saw rapid advances in understanding cellular electrolyte transport mechanisms. The discovery of ion channels and pumps revolutionized our comprehension of how cells maintain electrolyte balance. Development of flame photometry and later ion selective electrodes in the 50s and 60s enabled precise measurement of electrolyte concentrations, leading to better understanding and treatment of electrolyte disorders. The modern era has brought sophisticated techniques like patch clamping and molecular imaging, revealing intricate details about electrolyte movement at the cellular level and enabling targeted treatments for various conditions. Animals have evolved diverse mechanisms for maintaining electrolyte balance across vastly different environments. Marine mammals, for instance, have specialized kidneys that help them process high salt loads, while desert animals have extremely efficient systems for conserving water and electrolytes. Migration patterns of many species are influenced by electrolyte needs. Monarch butterflies seek out mineral-rich mud puddles, while many mammals travel long distances to reach natural salt licks. Different species show remarkable adaptations in their electrolyte processing abilities. Amphibians can absorb electrolytes through their skin, while some birds have specialized glands to excrete excess salt. The role of electrolytes in animal behavior extends beyond basic survival. Many species use electrolyte-rich resources such as social gathering points, and some animals can detect prey through subtle changes in environmental electrolyte concentrations. Climate change and habitat alteration are affecting animals' access to crucial electrolyte sources, potentially impacting migration patterns, breeding success, and population dynamics. Conservation efforts increasingly consider the importance of preserving natural electrolyte sources, recognizing their vital role in ecosystem health and animal survival. Electrolytes are fundamental to numerous industrial processes, from electroplating and metal refining to battery production and water treatment. The global market for industrial electrolytes continues to grow as new applications emerge. The battery industry relies heavily on electrolyte technology, with different formulations enabling various battery types. Recent advances in solid-state electrolytes promise to revolutionize energy storage capabilities. Electroplating processes use carefully controlled electrolyte solutions to deposit metal coatings on various surfaces. This technology is crucial in manufacturing everything from jewelry to electronic components. Water treatment facilities use electrolyte-based processes for purification and mineral balance adjustment. These systems help ensure safe drinking water while maintaining appropriate mineral content. Industrial cooling systems depend on proper electrolyte balance to prevent corrosion and optimize heat transfer. This application is particularly crucial in power plants and large manufacturing facilities. Emerging technologies in fields like 3D printing and nanomaterials are finding new uses for electrolyte solutions, pushing the boundaries of what's possible in industrial application. Food scientists work extensively with electrolytes to enhance flavor, improve texture, and extend shelf life. The interaction between different electrolytes can dramatically affect food properties and stability. Fermentation processes rely heavily on electrolyte balance, affecting everything from cheese and yogurt production to pickling and sauerkraut making. The right electrolyte environment enables beneficial bacteria to thrive while inhibiting harmful ones. Modern food preservation techniques often involve precise electrolyte management. This includes both traditional methods like salting and brining, as well as newer technologies using modified atmospheric packaging. The texture and stability of processed foods depends greatly on electrolyte interactions. Everything from the mouthfeel of ice cream to the shelf stability of canned goods is influenced by careful electrolyte balance. Nutritional fortification often involves adding specific electrolytes to foods, requiring careful consideration of bioavailability and interaction with other ingredients. Recent trends in food science focus on reducing sodium while maintaining flavor and functionality, leading to innovative uses of alternative electrolytes and flavor enhancers. The belief that sports drinks are necessary for any exercise is perhaps the most common misconception. In reality, most moderate exercise lasting less than an hour doesn't require special electrolyte replacement. Many people believe that all electrolyte drinks are equally effective. However, the ratio and types of electrolytes vary significantly between products, and some contain unnecessary additives or excessive sugar. The myth that consuming extra salt causes all types of high blood pressure oversimplifies a complex physiological relationship. While some people are salt sensitive, others may not see significant blood pressure changes with salt intake. There's a persistent belief that cramping always indicates an electrolyte imbalance. However, muscle cramps can have various causes, including mechanical stress, fatigue, and nerve compression. The idea that you can't get enough electrolytes from food alone is generally false. A balanced diet typically provides adequate electrolytes for most people under normal circumstances. A dangerous myth suggests that drinking more water always helps with electrolyte balance. In fact, excessive water consumption without appropriate electrolyte intake can lead to dangerous dilution of blood electrolytes. Well, that does it for this episode of Food Truth. Thanks for joining me as we've taken our deep dive into the world of electrolytes. Join us on our next episode as we take a close look at the only rock we eat, also known as table salt. If you want more information, please visit us at www.getfoodtruth.com. Thanks for joining us. We'll see you next time.